So without further ado, let me introduce our first speaker, David Irwin. David Irwin is an associate professor in the Department of Electrical and Computer Engineering at UMass. He leads the Sustainable Computing Research Lab, which focuses on designing, building, and analyzing distributed software systems with a particular emphasis on improving their efficiency and sustainability. He currently serves on the steering committee of ACM E-Energy and the steering committee of ACM BuildSys. With that introduction, David, please perhaps share your slides, and the stage is yours.
Thanks, Omid. Let me just set this up here. Next slide. Okay, yeah, so thanks, Omid, for the introduction. So today I'll be talking a little bit about really a collection of work that we've done over a decade on solar performance modeling and forecasting, which we have kind of packaged together into a toolkit, an open source toolkit that people can use for this kind of to drive kind of work that requires the use of solar performance models or forecasts. We'll call it Solar TK. One second. Yeah. Okay. So we've been working in this area for the past decade, and we've in a number of different ways, right? So solar comes up in sensor networks or IoT systems where you're deploying them outside and you need a power source. So solar is really the best power source for these kind of off-grid systems for a variety of reasons. It's passive. It can be scaled down really easily, unlike wind. It keeps getting better and cheaper over time. And so really it's kind of the best renewable energy source for, really any scale of system. So we've done a lot of work in IoT systems, small systems, off-grid that need to harvest energy to continue operation. You're seeing solar a lot used in data centers, large-scale data centers, or even smaller scale data centers kind of at the edge that are also either off-grid or they want to reduce their carbon footprint. And this is actually a big focus of companies now. Google, within the last month, said that not only do they want to be, quote, carbon neutral, which essentially means that they fund a lot of large-scale solar projects to offset their grid energy usage, but they also want to be carbon-free now, right? That's their next goal for the decade. And carbon-free basically requires them to combine solar or wind with batteries, right? And so even these data centers and these edge computing facilities are looking to integrate solar primarily with batteries to run without any kind of carbon footprint. And then obviously you see it in the smart grid, right? Where we want to integrate more distributed solar on rooftops and solar farms, to reduce the carbon footprint of the grid. And so you see solar in all these different places, okay? And this is the kind of work that our lab does. We work in each of these different areas. And we're always kind of like, we're often not focused directly on the solar, but any kind of performance, efficiency improvements, we always need to know, how much energy is going to be produced kind of now, and how much will be produced kind of in the near term future, and even over the long term, what kind of energy can we expect when we're doing capacity planning, right? So, being able to model solar performance, its output based on, the current environmental conditions, and to forecast into the future is just a very common thing that comes up. So the point is that, it comes up all the time. And you would think it would be kind of a settled thing, like we could just go off and download some toolkits or some code models that just do this. And to some extent, you can, as I'll discuss, a lot of the models exist, but for the kind of work we do, they weren't packaged in the right way, and they really couldn't be used directly in systems that we were building. And I'll explain a little bit about that, why that is. So the challenges with solar modeling and forecasting is that solar generation is dependent on a large number of different variables, right? And so, I've listed some of the variables here. The solar irradiance, obviously changes over time based on your location on the Earth, the time of the day of the year. The incident irradiance, the amount of sunlight that actually strikes a solar panel, differs based on that panel's tilt and orientation. The temperature of the panel affects how much, what fraction of solar radiance can be converted to electricity. Obviously, different solar panels have different actual efficiencies based on like the internal construction and materials that the panel uses. There's all different kinds of solar panels. There's also shading and soiling from surrounding structures, trees, or from snow or dust that build up on panels. There's various electrical losses that occur when you convert the DC power of solar into AC if you're using AC. So, different types of inverters, microinverters, centralized inverters, how the panels get wired together, right? All of these different things affect solar output, right? And so this makes solar performance modeling and forecasting challenging because, you really have to, if for a lot of our applications, we're looking to model solar for a single site, right? So for one site with, particular attributes. And so for modeling those sites or those systems, we need to really develop a custom model based on, its efficiency, the cell temperature, the temperature coefficient, the tilt and orientation of this system, how the inverter is for this system, how it's wired. And, these variables, there are some that are static, right, that are fixed, like, I guess often tilt and orientation are fixed, although they can change. Some are dynamic, like the environment, right? Shading and soiling is dynamic and changes over time. And so you have to be able to kind of track those changes. So this is kind of all the different things to consider. Now, this is an area of, a ton of work, right? And so for most of the variables on the previous page and for most of all these different, things that change, there are good physical models that exist. The module type, how the tilt and orientation affects the translation of irradiance into electrical power, what the temperature effects are, what the inverter losses are. All of these variables, there are really good physical models to predict them. In some cases, very specific. Like, there are toolkits where, you kind of can select your specific inverter and it will give a model for that specific brand and, of inverter. There are some variables that lack accurate physical models. I'll mention snow is one of them, which we've worked on recently because in Massachusetts, where I am, it snows a lot, has a huge impact on solar performance in the winter. So they're not great physical models for those, in part because snow is, in particular, also dust buildup, is just complex. It's hard to model. But, there are people that study this kind of modeling and forecasting in a wide range of fields, right? So in atmospheric sciences, mechanical engineering, environmental engineering, there are actually, people who focus entirely on solar modeling and forecasting. In fact, this book down here is actually a great book, Solar Energy Forecasting and Resource Assessment. There are really just tons of papers and textbooks on this topic. There's some difficulties, though, in translating all of that research into, something we can just use when we're building systems that need solar models and forecasts, right? So one is that there are very few open source implementations that do both irradiance modeling and forecasting and solar modeling and forecasting, right? And so most, as I'll discuss on the next slide, most open source code assumes that it's fed the irradiance. And given the irradiance at a location, it has all the models for the tilt and orientation, the module type, the temperature effects, the inverter losses. And then, so most work in this area kind of divides into that. There's the electrical system piece of it. Then there's the irradiance forecasting piece of it. There's few open source implementations that combine both. if any, that I know of. And there's the irradiance forecasting piece it turns out to be hard, and not very open. So it's not like you can download really good irradiance forecasts from anywhere that I know of for free. And then it's not trivial to re-implement this stuff and like how you do it, right? It's difficult and time consuming to re-implement. We started maybe a decade ago when we just kind of needed this stuff, needed some good models and forecasts. And we used kind of some basic machine learning techniques about a decade ago. It's actually the stuff we were doing back then was very rudimentary. It wasn't really using any physical models. It was just using machine learning directly. That work, actually, it's highly cited. It's not particularly good. We've done a lot since then, and that's all been packaged up into the Solar TK. But, what's interesting is we actually see that work used a lot, right? So I'll see it in, papers at top conferences recently that need solar models and forecasts that cite this work we did like a decade ago, and say that they're using kind of the same technique. And it's a simple technique, kind of doing some straightforward machine learning, but it's not particularly accurate for a variety of reasons. And part of it is that, using machine learning on something where there's so many good physical models available just isn't going to be as good as using the physical models. And then, for irradiance forecasts too, like you can get good forecasts if you buy them. So there's some companies that do provide some good irradiance forecasting, but it's not accessible to us for free. Okay, so here's some, there's a lot of work in this area. These are some different types of models that are available, toolkits, code that's available that you can get for doing this kind of modeling. Most of these are what we call white box models. So, in fact, PlantPredict, PVlib, and SAM, which is the system advisor model developed by NREL, are all white box. So basically, you open these things up, you go in, and you configure your system. You have a system, you know everything about it, the brand and serial number of the panels, how they're wired together, what inverter you have, where they're located, what the tilt and orientation, you know all this stuff. You configure it in this system. And then, you get irradiance data from somewhere, okay? It doesn't really, that's often not stated how you get the irradiance data. You just get it from somewhere. Oftentimes, these aren't used for like kind of in systems for real-time applications like we use them for. Like, for example, NREL, which does the system advisor model, it's mainly focused on like, economic assessments of whether solar is a good investment or not, right? And so what they're often doing is, configuring a system that maybe doesn't exist yet to see, on average, how much it'll produce over the next 25 years, right? And it'll use a typical meteorological year's irradiance to do that, right? And so some of the applications here are just a little different than what we want to do, which is actually have live, real, custom models and forecasts. The other thing that, a lot of these, some of these are proprietary. So PlantPredict's proprietary. So we actually haven't used it because we haven't bought it. It costs money. There's some other differences. Some are programmatic. They have data interfaces, as well as some have GUIs, like SAM has a GUI that you can use. SolarAnywhere actually doesn't do solar, the electrical side. It does the irradiance side. So what it does is translate satellite data into irradiance predictions, irradiance inferences of surface irradiance and irradiance forecasts. But none of these really, the point is, none of these kind of really fit our needs. They're hard to configure, right? So if we want to go and try to, we often use PVlib, we'll try to configure it for our systems. We have to know everything about the system to configure it. Once we configure the panels, then we need to get a radiance data from somewhere, right? And actually, PVlib doesn't really include it in their models. They have some irradiance forecasts that they'll use, but they don't have any models. So we have to figure out how to get irradiance, infer irradiance for it anyway, even after we configure it. So they're not very easy to use, and they don't really combine this irradiance with the actual system very well. So what we did was basically develop this solar TK with these goals that really fit our needs. So the goals were, we want it to be simple to use by researchers that aren't expert in solar. Most of the systems we have already exist. So we want to be able to just build the models given some small amount of historical generation data. We want to be able to make it extendable so that we can include models for things like snow or maybe improve upon it and kind of break it down into its constituent components so that we can use it for research, for different types of analytics. We actually went somewhere in between a GUI and an API, a programmatic interface. We actually made kind of modules that connect via Unix pipes, where each module does a specific thing. And we did that because we found over time in our research that these different modules kind of came out of our research as things we were doing over and over again, right? And so it kind of naturally kind of divided into these modules. And we publicly released it as open source on GitHub, along with a bunch of solar data. And it can just be used, right? We just use it. It gets, weather data off of Weather Underground. It kind of incorporates all these physical models inside of it. Its input, its data. So let me just get to kind of the pipeline here. Like I said, it's basically a series of modules, Python programs that are connected via Unix pipes, right? So this is kind of the basic pipeline here, which is we have this first module called the physical parameter module that uses data, takes its input to data, and then spits out the physical parameters of the system, right? Its estimate of its area, its tilt, its orientation, temperature coefficient, things like this. It sends those physical parameters that it can be served as input into what we call a maximum generation model. And what this does is spit out, using a physical model, a known physical model, based on the physical parameters, an estimate of this system's maximum generation at any given time based on its location. And then that gets piped over to what we call kind of a weather-adjusted generation module, which basically uses, the weather forecast or the actual weather to adjust the maximum generation to understand kind of how much it decreases based on the weather, clouds basically, and actual temperature. And there are some more models kind of some more modules kind of downstream of this, but these are kind of the main ones. So here I'll say a little bit about each one of these modules. So the idea behind the physical parameter module is we're going to get as input some data, some solar data. The amount of data kind of doesn't have to, it varies how much you need to get kind of an accurate model. It doesn't have to be that much, right? Probably, if you're given the location, probably 2 days of data, as long as it's sunny for those 2 days, will generally give you a fairly accurate model. And what we try to do is fit to this equation here, which is kind of a big, long equation with a bunch of sines and cosines and angles. And what we're trying to do is find these various parameters here. So beta and this phi are the tilt and orientation of the panel. These two, theta and I guess alpha, are the sun's position in the sky, which is a function of location. So right now we assume that we're given the location. We actually have work that we hope to work into this toolkit where you actually don't need the location. If you have enough data, you can basically infer the location and these angles without being given the location, but we don't have that now. And then K is kind of a product or a combination of the size of the system, and its efficiency. And the idea here is that for any given location, solar, the actual clear sky irradiance is going to vary based kind of on a solar curve that's well known, that can be, is deterministic, how the clear sky irradiance varies over time for a location. And in this equation, given that clear sky irradiance, which is this equation dictates how much solar power there will be given efficiency, the tilt, and orientation of the panel. And so what we want to do is actually take the deterministic equation, or the deterministic clear sky irradiance over time, and we actually want to fit that curve to the actual solar data that we see by finding values of these variables. And actually, I say fit, but we actually don't want to fit it. We want to upper bound it, right? Because basically, it's kind of like, the figure in the lower right is a good example, where we want to, that clear sky irradiance plus these variables represents the maximum we could ever produce. So we want to find values of K, beta, and phi such that the upper bound of that, such that it's the tightest upper bound on the actual data that we have, right? And as long as there's at least one sunny point where it was clear skies in that data, then that one point will bound the entire curve and kind of give us a good estimate of K, beta, and phi, all right, which is the tilt, the orientation, and the size and the efficiency of the system. Now, this is an estimate, right? So we're making some assumptions here. We're making an assumption that it's a single plane, right? Not all systems are a single plane. We're making kind of an estimate that we're effectively assuming here implicitly that we're using microinverters if we're converting to AC, and the panels aren't kind of wired together in a weird way. We can correct for these things downstream a little bit, and I'll say a little bit about that. But right now, we kind of make these implicit assumptions. All right, so so here's the interface to it. Basically, the input, it's command line interface. The input is your location, latitude, longitude, some data in a CSV file. And what we output is the latitude, longitude again, the area, the tilt, the orientation, the temperature coefficient, and what we call the base temperature for the panel. And so you can see kind of down here the output of this. So we evaluated this, probably need to speed up here. Basically what we see here on the right side is we have pretty good accuracy. This is ground truth for size, tilt, and orientation. We find them fairly accurately, all right, with just a little bit of data. The next module we have is what we call the maximum generation module. And the key here is we pipe in these parameters to it, right? And what it does is it just applies the equation along with this adjustment for the air temperature, and will spit out the actual generation based on those parameters, right, at a given time in kilowatts. So you can see it here. The parameters get piped in. And then to this max gen, you give it a resolution. We can do any resolution, the start time and the end time, and it just dumps out the maximum generation. One important point here is we don't need to use that parameters module. If we know the parameters, we can just pipe it directly into this max gen model. So really the learning the parameters from the data is kind of separate from now kind of applying those parameters to estimate the maximum generation. And that turns out to be useful because in some cases we do know the parameters. We don't need to learn them from data, or if we want to estimate them based on a future system. So we evaluated this maximum generation model. We actually compared it with PVlib. We went around to sites where we either had access to or could kind of infer the actual information of these sites. We configured them in PVlib, and then we used data. We had data from these sites. We used the data to build a model of the maximum generation from SolarTK. And what we see here at the bottom is the error, the mean absolute percentage error between SolarTK and PVlib is pretty similar, right? So again, PVlib, basically you go in and you configure everything from known data. Here, we're just kind of learning these models from a small amount of data. And we end up doing, essentially similar. In some cases, we do much better. In some cases, maybe we do a little worse. Higher is worse here. So in these, we do a little worse, 2 and 3, and 13, 12, 11, 10, 9, we do much better. And that's to some extent expected because we're actually learning a model from actual data where PVlib does not do that. Okay. Let's see. Then next we use a weather-adjusted model. Okay, so what this does is take the maximum generation and then adjust it based on effectively the clouds, right? And how much irradiance gets blocked by the clouds. The way we do this right now is we just take weather data from Weather Underground. It's pretty bad data. We take forecast data from the National Digital Forecast Database in the United States. It's pretty bad data. It basically gets cloud cover as like a string, like overcast, broken, scattered, clear. It turns out that there are models from 30, 40 years ago that translate those into what's called a cloud index, the fraction of sunlight that gets blocked. We've tried to improve upon those models a little bit, but the data is not great. So we use a function. This is kind of a slightly modified function from one that was empirically fitted a long time ago and kind of very well-known work. And so, but what this provides us is some estimate of the current or the forecasted actual generation of the module. Okay, the errors here are much higher because that data, the cloud estimates are really not great, right? But again, we see we do as good generally or better than PVlib without having to kind of go in and configure all of PVlib's stuff without knowing anything about the panels. We have a few minutes here left. Yeah, so I already said this. We can adapt SolarTK, so we don't have to use a physical parameter model. We can just specify those parameters. It's pluggable, so we can add new things. So like one new thing we've added is what we call a shade adjustment module, right? So like, none of those other modules I talked about accounted for shading from trees or from buildings. Well, shading is unique to every solar site, right? So you actually, our shade adjustment model uses machine learning to train, a model custom to each site. It takes more data to do that. But what's interesting about it is we can use SolarTK to basically do feature engineering on the input, right? So, the input is the sun's azimuth and zenith angles, the position of the sun in the sky. And the output variable is like what we expect the solar output to be from the weather adjusted generation module as a ratio of what it actually is, right? And if the ratio is 1, it means there's no shading. What we thought was going to happen, it happened. But if it's a lower ratio, then that means there are potentially high shading based on the sun's position in the sky, right? And so we can learn that. I won't say too much about snow. Snow's a big deal. We actually have a paper in BuildSys discussing snow. It's really hard because there's no physical models for it, but it's very important, very, very important in high latitude places like Massachusetts. I said the weather adjustment module is not very good because the data that it's using is not very good. You can do much better with satellite data. We also have a paper in BuildSys discussing using satellite data. It turns out the US just launched within the last year or two some new satellites that give like great multispectral data of the Earth every 5 minutes at very high spatial resolutions. You can do a lot with that to improve estimates of surface irradiance to get better models. Yeah, so let's see, I have a couple minutes. I'll just say a couple of things here. I won't go in depth into these case studies, but we use this all the time, right? So we used it for this case study that my colleague was working on in estimating solar in Kenya. In that case, what we were doing was using the maximum generation module to understand what the solar potential was for a bunch of homes in Kenya that use little solar boxes, like solar kits with small solar panels. We've used it for some of our disaggregation research. Basically, again, the key there is that when we want to disaggregate solar from electricity consumption, when they're kind of combined together, electricity consumption acts a lot like clouds in that it decreases what we view as the solar output. And so, but that doesn't matter because we can build these models of maximum generation regardless of the cloud cover because they're bounded by the peak solar time. And then we can just apply the weather adjusted generation module. And then finally, one other way which we can like replace the weather adjusted generation module, instead of getting kind of the cloud effects from a weather site or a weather forecast, right? We can actually, if we have a nearby solar panel, right, it can act as a kind of a parameter to give us an estimate. And so we've used the toolkit to basically reverse engineer kind of that cloud index or that cloud fraction from other solar sites. So I think my time is up here. So I won't go into much more. Just to say that we do have a public release of this, so people can use it. We have a bunch of work that's been published over time on it. So we have the code, we have the data. The main student that's been kind of doing all this is Noman Bashir. So he's kind of the best contact person for it. And then here's the GitHub link. So I'll stop there if there are any questions.
Perfect. Thank you, David. We have time for a couple of questions, I believe. So you can either write in the chat box here, or you can write it in the Slack channel for ePerf workshop, and I can ask it from David, or you can just call your name and you can unmute yourself. Either way would work. Okay, so there is a question in the chat box.
Yeah, so how accurate does the location information need to be? I don't know. I mean, we haven't done that analysis per se. I mean, we usually know the exact location, so we just plug them in exactly. I would just think that if you had a city location, it's probably going to be pretty good. Like probably within 50 miles, whatever that is in kilometers, is probably okay. Yeah, but we haven't done that analysis per se.
So I also have a question, David, regarding the resolution of irradiance data. I know that there are some sites that you can buy a license and get more or finer granularity data for solar irradiance. Have you tried using different time resolutions to see if it changes things at all?
Well, so a couple of things. The maximum generation model isn't based on any irradiance data because it's just using a clear sky library, clear sky irradiance library. So it can produce data at any resolution. Mm-hmm. The weather adjusted generation is what we currently have is based on the resolution of the data that the irradiance data comes from, or the weather data comes from. Actually, we can do higher resolution, but all we do is extrapolate from that. We basically say, like, if it's an hour resolution, we say the whole hour is that, is whatever they told us the kind of irradiance estimate was. If we bought irradiance data, or we were able to get it from like SolarAnywhere, we would basically make a new module that was like our satellite-based module. I mean, effectively what SolarAnywhere is doing, or like other, SODA, I think, is another one that does satellite estimates, is they're just taking the satellite data that we're now getting publicly from NOAA and applying a model. Mostly they apply physical models to it. We've been kind of applying some machine learning models to that raw data. And it does much better. I mean, it's much more accurate. even at, at 5 minutes, an hour, it's more accurate, significantly more accurate than the very coarse cloud cover data that a weather site will give you. But I can't, off the top of my head, tell you how much, but it's at least 2x more accurate.
Perfect. And there is one more question in the chat. It's regarding SolarTK.
So what are the next step plans? Right. So we have this snow work that I don't think is integrated fully yet, although the paper is going to be presented next week. We'd like to integrate that. That's the near term. The satellite work, really, we'd like to integrate the satellite work, which is currently modeling work, not forecasting. Modeling is inferring current solar generation based on current conditions. Forecasting is predicting the future. We'd like to eventually get the satellite work and the model and the forecasting, importantly, in there, because that, I think, going to improve the results a lot. The accuracy, that's really where that accuracy is. And long term, I really would like to take some of this work we've done on inferring location from data to allow people not to have to spit in a location, right? So then it's just, you spit in data and then out comes the model, the estimates of maximum generation, the actual weather, the forecast of everything. So it's really just kind of hitting a button. But there are some challenges that inferring the location gets hard. You need much more data for doing that. Like and how much data you need a year. Can you do it with less than a year is hard to say right now.
Great. Thanks, David.